Hey students, welcome to STEM Renaissance. Today we'll be summarizing Unit 2 and 3 of AB and BC Calc, which is differentiation.
So first of all, I hope you all are familiar with this. If not, please review it and make sure you know your derivatives by the time you take your AP exam. And I know this is quite overwhelming, but that's why we're here for you. Let's look at the next page. Oops. I don't know who made this page, but we'll skip it anyway. Based on my experience, College Board won't expect you to memorize all these derivatives either, but at least make sure you know the basic ones. Even though you can remember all of them, please keep in mind, you will always be able to derive some derivatives from the other. For example, when you know the derivative of tangent, you can use the quotient rule to find the derivative of cotangent easily. And for the inverse trig functions, you can use a technique called implicit differentiation, which we'll discuss in this video to find them. The technique we're going to discuss today is called implicit differentiation. So implicit differentiation allows you to find the derivative of y with respect to x without having to solve for the equation y explicitly. In fact, implicit differentiation still gives you this relationship between a set of variables, while the only difference is one might find it really hard to turn an equation into the form y equals f of x. And when this happens, implicit differentiation can be much more powerful and sometimes the only way to find the derivative, as you will see. So the last topic of the day will be the relative rate problem. The way to tackle this kind of problem is fairly straightforward. First of all, identify the relationship between each equation. For example, the relative velocity between your dog and your cat, of that kind, whatever. Then simply take the derivative with respect to correct quantity. I know this sounds quite stupid and even just so trivial, but really, believe me, sometimes people will take derivative just randomly even before they know the meaning of each quantity. So please avoid that. And now it's time for today's problem session.
Okay, so this problem, we're finding dy dx by implicit differentiation. To start this problem, we have to take the derivative of both sides with regards to x. For the derivative of the left side, we simply get 0 plus 1. Notice that in order to solve the derivative of the right side of the equation, you have to know the chain rule, the product rule, and the derivatives of trig functions. Let me emphasize this a bit. You have to know those rules. So when we take the derivative of cosine x and y squared, we get negative sine x and y squared for the outer function. And then, according to the product rule, we get 1 y squared plus x 2y dy dx.
Oh, I have a question. Why do we need to multiply dy dx here? Why not just x 2y?
Good question. The truth is, we have to assume y is some function of x, and we have to apply the chain rule here again. By applying the chain rule here, we get 2y, which is the outer function, and multiply the derivative of whatever y is, which is written as dy dx. Now, we just have to do some simple algebra. Keep in mind that our goal is to isolate dy dx on one side of the equation. So we first divide negative sine x and y squared on both sides. So on the left side, we get 1 over negative sine x and y squared. On the right side, negative sine x and y squared divided by itself is just 1. So we just get y squared plus 2xy dy dx. Then we can simplify the left side of the equation to negative cosecant x and y squared. By doing the rest of the algebra here, we get negative y squared minus cosecant x and y squared divided by 2xy equals to dy dx. Let's look at the AP problem that is related to these two units. You can pause this video to try this problem on your own. Part A is a pretty straightforward problem. Like any problem that you need to find an equation for a line, you need to know a point and the slope. In order to find the slope, you just need to plug in the point, negative 1, 1, into the derivative of the equation, which is dy dx. So dy dx at the point negative 1, 1 equals 1/4. Since now we know the slope and the point, by using your knowledge of the point-slope formula, you get the equation. Part B. So for part B, you need to ask yourself, when will the line tangent to the curve be vertical?
Ooh, I know. The line tangent to the curve is vertical when the slope is undefined.
Yep, you're right. So the key to solve this problem is to set dy dx to be undefined, which is setting 3y squared minus x to 0. From the problem, we also know that y cubed minus xy equals 2. To solve this system of two equations, we get x equals 3 and y equals -1. Therefore, the tangent line of the curve is vertical at the point 3, -1. Now, let's look at part C. Okay, so finding the second derivative is just like finding the first derivative. First, we take the derivative of both sides of the equation. So on the left side, the derivative of the first derivative is just the second derivative. Notice on the right side, we need to use the quotient rule. By using the quotient rule, we get the following equation. Since we know from part A, dy dx at x equals -1, y equals 1 is 1/4. Now, by plugging in 1/4 into the equation, the second derivative at the point -1, 1 equals 1 minus 1/2 over 16, which is 1 over 32. For relative rates problem, first, we want to establish some relationships. Keep in mind that we already know dh dt. Our goal is to find d theta dt and dA dt. The first part of the problem asks what rate is the base angle changing when h equals 1, when h equals 4, and when h equals 8. Therefore, first we need to establish the relationship between h and d theta dt. Let's look at the diagram on the left. Notice there's a triangle involving the base angle and the height. We also know the two sides of the triangle. Therefore, we can establish the relationship between the base angle and the height, which is tangent theta equals h over 2. Since we want to find the rate of the base angle is changing at certain heights, we want to take the derivative of both sides with regards to t. The derivative of tangent theta with regards to t is just secant squared theta times d theta dt. On the right side, we simply get 1/2 dh dt. By isolating d theta dt on one side of the equation, and by plugging in 3/4 for dh dt, we get 1/2 times 3/4 times 1 over secant squared theta, which can be simplified to 3/8 cosine squared theta. Since we want to find what rate is the base angle changing when the height is 1, when the height is 4, and when the height is 8, we want to establish the relationship between the height and d theta dt. Going back to this equation, we can isolate the angle theta to equal to tangent inverse h over 2. Therefore, d theta dt equals 3/8 cosine squared tangent inverse h over 2. Finally, when h equals 1, the base angle is changing 0.3 radians per second. When h equals 4, the base angle is changing at a rate 0.075 radians per second. When h equals 8, the base angle is changing at a rate 0.022 radians per second. The second part of the problem is really similar to the first part. Now we just have to establish the relationship between the area and the height, because we are finding what rate is the area changing. The area for the trapezoid is just 1/2 times base 1 plus base 2 times h. Since the top base and the bottom base are constants, we just need to plug them in. By simplifying this, we get A equals 14h. Since we're finding the area is changing at what rate, we need to take the derivative of both sides of the equation with regards to t. This is a fairly simple implicit differentiation, so we get dA dt equals 14 dH dt. By plugging in 3/4 to dH dt, we get the area is changing 21/2 centimeters squared per second.